The title of my today's talk is When Fluid Mechanics Meets Biology Revisiting Smallpox, a Modeling Framework for its Airborne Transmission. I am Mohammad, Mehedi, Hasan, Akash. Almost every aspect of respiratory transmission may be traced back to fluid mechanics. The work that I am going to present today, it is going to be a combination of fluid mechanics understanding of transmission with the corresponding biology data. And for biology data, we will use exposure time of the virus and the viral concentration load. This framework modeling has already been introduced by ourselves on SARS-CoV-2 virus and which has been already published in scientific reports. For today's talk, I use the biologic data of smallpox. The virus causes the smallpox is variola virus, which falls into the pox virus family. The other members from the pox virus family are monkeypox virus and the vaccinia virus. And next question, why are we revisiting the smallpox virus again, which one is already declared by World Health Assembly to be eradicated in 1980? Because the monkeypox outbreak is widespread and there are almost 28,000 confirmed cases in the USA as of November 3rd, 2022. And because we are currently have few virologic data for monkeypox, I use the smallpox virus to create a framework that is applicable to all other members of the pox virus family. Now, smallpox spreads through the airborne droplets or aerosols of saliva from an infected person, and it can be spread by other ways, and that's why we can call this as an anisotropic infection. It should be noted that I will not distinction between aerosols and droplets during this presentation. Rather, I will refer to all liquid particles or particulates as droplets throughout this talk. Two main questions I am going to introduce in this talk. First one, what are the hazardous droplet sizes that can start the infection? What is the infectious dose? Infectious dose is the minimum number of virus that can trigger the infection of an individual. To answer these questions, we first think what we know about this virus. We know that the infected zones of the smallpox virus are the oropharynx and the lung. Oropharynx is marked as red in the visual of subject 1, and subject 1 is the CT scan based anatomic reconstruction. The oropharynx is the part of the pharynx behind the mouth. It consists of walls of throat, tonsils, last third of the tongue, and the soft palate. The lung has been shown as outlet, which is marked as lower airway. Here, particle will be penetrate through lower airway to the lung. As these are the initial infected zones, for answering the first question, that what are the droplet sizes which are going to land directly at the oropharynx and going to penetrate through the lower airway to the lung during our breathing process. So in order to figure that out, I simulated our breathing rate over a wide range of 15 liters per minute to 85 liters per minute. When we are sitting and breathing in a relaxed way, we typically breathe at 15 liters per minute. When we inhale intensely, our breathing rate goes up. All the airflow simulation ran as LES and we used ANSYS Fluent as a solver. Against the simulated breathing rate, I tracked droplet sizes ranging from 0.1 to 55 microns. I selected these particles ranges and inhalation rates from our previous published work on SARS-CoV-2 virus. The density of the droplet material is 1.3 gram per milliliter, which is slightly lighter than the density of water, as these are the dehydrated respiratory ejected droplets from infected persons. This horizontal axis in this graph represents the tracked droplet number sizes. This graph shows that the size range of which direct oropharyngeal deposition occurs is approximately 5 to 49 microns. What made me stop at 55 microns? Actually, these are the expelled droplets by infected individual and then undergo environmental dehydration. Now, if the droplets are any bigger than 55 microns, they will undergo prompt gravitational desorption and probably won't be that effective to launch the infection in some other exposed subjects. Let's do a quick check on these sizes using the Stokes number equation and simple scaling analysis for the two different flow rates and all other flow parameters remaining same. We can show that the flow rate is inversely proportional to the square of the diameter. It means that at higher flow rate, particle will hit the wall zone earlier than the lower flow rate. It is happening due to the high inertia from higher flow rate. This slide shows a graphic representation of the predicted droplet size distribution at oropharynx, and we are considering that there is at least 5% oropharyngeal deposition. CFD droplet size ranges are represented by deep colors and the Stokes number projected ranges are represented by the light colors. Let's discuss the first panel as an example. In this panel, we are going to predict the droplet size range for 15 liter per minute using CFD values of 30, 55 and 85 liter per minute. First, focus on the trend of droplet ranges from CFD. As all other inhalation rate in this panel higher than 15 liters per minute, so the trend line for CFD should move left to the orange deep line, and it is happening. And we can see it if we focus on the black, deep blue and the deep green line. Now focus on the light oranges in the first panel, and they are representing the size range for 15 liter per minute but using CFD values respectively for 30, 55 and 85 liter per minute. So what should be the trend? As for this case, we are predicting lower flow rate using higher flow rate. The projected range value should be higher than the CFD value, so they should move right from their CFD line. Similarly, in the first panel, we are predicting Similarly, in the last panel, we are predicting higher flow rate using lower flow rates. So Stokes projected size ranges, light green lines, all should move left from their CFD lines, and that is happening. In the other two panels, second and third one, there is the same trend we can look for. As we mentioned earlier, the lung, which is shown as lower airway, is also an infected zone for smallpox. Approximate hazardous droplet size range at lower airway is 0.1 to 15 microns, which is actually less than 15 microns. And we can see a monotonic trend in lower airway, so that's why we are not going to do any Stokes number projected size calculation for lower airway. To answer the second question, what is the infectious dose of smallpox? Infectious dose is the minimum number of virions or particles that can trigger the infection of an individual. We calculated that infectious dose range for lower airway is 400 to 4000, and for the oropharynx it is 4000 to 40,000, and which is supportive to the literature review what we get from Milton 2012. And the infectious dose range also supports our literature review, which is order of 100. Noted that smallpox virus concentration is 10 to the power 6 to 10 to the power 8 plaque forming units per milliliter. The particle distribution range for higher virion transmission in lower airway and the oropharynx are respectively 11 to 21, and for oropharynx it is greater than 41 microns. The particle tracking is also ongoing when particle is entering from the mouth opening, and this is ongoing work for the oropharynx deposition and the lower airway. In future, we are going to apply this framework to another two subjects, subject 2 and subject 3, which are also CT-based anatomic reconstruction. Thank you for your attention.